Alright, so we're back, and it didn't take too long. Easy peasy, lemon squeezy. Okie dokes. So what are we looking at here? I got a lot of paper here. This is what I'm looking at, all these 3 pages. So you only need to see this one, really. Okay, so we had it such that... Oh, they're just a negative of the other. It's just an invert. One starts at 1, one starts at 0. One starts at 1 and one starts at 0. Something doesn't make sense here. One and 0. Okay, fair enough. Why not? We're saying in pi over 2. Pi over 2 phase. So we wanted to find out what's happening in pi over 2. And basically at pi over 2, we have 1 at 1. We have this. So this is what's going to happen when we're out of phase. And this is the actual sinusoid. This is not our distribution. Okay? If we launch the sinusoids out of phase, if we launch one sinusoid like this, sorry, that's cosine, one cosine like that. We launch another cosine out of phase, 180 be like that. Right? Am I right or am I right? Of course I'm right, all the time. Even when I'm wrong. Even when I'm wrong. I digress and I continue. Okay? So we can also say this is continuing here, basically. And there's our 2 cosines. There's our 2 cosines like that. Now they're saying something strange here. They're saying that at pi over 2, pi over 2 here. At pi over 2, we get a 50-50 shot. And that's this basically plus this divided by 2, right? Sure. Bizarre. And here at pi, we have 0.1. So this is when they're pi over 2 out of phase. And that's just add these two, they should be the same. Right? Then at pi, but it's 1 minus and 1 plus. Why do we change it to plus? One's cos. This is just cos. No, I drew them out of phase already. The average is always going to be. Why is the average turning out like that? Why is the average turning out like that? And why do we switch them? Why do we go plus minus? That's because the mirror, I bet, reflection I'm trying to tell you about. And this one, and then this one. And these two subtract, divide by 2 here, and on and on. Not this. This is nothing. Right? We have 4 cases, basically. And then it aliases. No need to consider other. Anything else. No need to consider anything else, really. Here and here. Okay. And that looks pretty freaking even to me. It does. I don't see anything other than a 50% chance of it hitting here or here. Why are they telling me otherwise? I don't know. I don't know. On this side, we just added them so we don't get a negative energy. We just said plus to make it up here, I think. Shift the result up here so we can demonstrate mathematically. We know this is not. There's something in that when you take the imaginary, it's like here or something, right? You deal with the imaginary number, it's like this. We just generally have a 50-50 chance of it landing. Right? Easy. Easy peasy lemon squeezy. It's just an average. But D2 demonstrates that this is D2. This is with the pi over 2 phase shift, right? Did I shift those pi over 2? Basically. Now let's look at a pi phase shift. What happens when you do that? If this is sinusoid, I don't care. Sinusoid, cosine. Doesn't matter to me. They're the same. Why? Because I'm like that. And I don't mess around. And I know them like so well. And they're like the back of my hand, basically. Okay. Now here we go. Here and here. Now this is a different phase shift here. This is a pi phase shift. We're doing the same thing. So we have when we have a pi phase shift, we have 0 observation period for N1 and N2. And when we do it here, we have pi over 2, we have a 0 phase shift. I mean a 0, you add them, divide by 2, doesn't matter. It's too late, they're already 0. Already 0, already 0. So what are we saying? D1 is this. No, we're not dealing with detectors yet. Now let's look at the detectors. Now let's look at the detectors here. Let's see what they say. Pi over 2, they said it would be N over 2. And we just looked at that and we saw that. Pi over 2. Pi over 2. But here it says it's 25/75 when you plug it in the equation. These equations, which is weird. 0.75. I don't know why. I'm trying to work. I'm just hacking at this. This is how I hack. It's not really the most efficient. I'm not the most efficient dude at doing these things. This is what should be happening if it's a wave. Man, it should either constructively interfere or it should destructively interfere. Like, it's common sense. And if it constructively interferes, it should be occurring here. This is with the how many what did I shift it? I think I shifted it this time. Pi over 2. I had a pi over 2 phase shift, and now this time I have a pi phase shift. So we're looking at this situation here, but it's saying what we actually observe here is that 100% of them are landing on N1, this one. Okay, fair enough. Right, and then, but when they're perfectly in phase, we do this. And we have another one like this. 100% of them. This is just a matter of you know what's causing it? You know what's happening? Nothing. Nothing's happening. I'll tell you what's happening. There's nothing to do with the fact, except for the fact that we're reversing the mirror. The mirror reverses the polarization. And polarization, I believe in. Not interference. Not interference. A spin. A spin on the photon. It's going one way, it hits one going the other way, and something happens. Something happens. Something happens that when it's polarized, something happens when the polarization hits. It's not about interfering waves. It's about polarized particles. Like we can like it's so obvious. They're polarized. Polarized light, for example. That's the way we do optics, with polarized light, not with interference. There's never any interference with lights. Don't tell me that. Don't tell me it's interference. Water is polarized. Molecules are polarized. Atoms are polarized. No, maybe not. Okay. But electrons are polarized. They have a spin. Up or down. Okay? You see what I'm saying? Use your head. A scale. Nothing. Good and evil. You can't beat God. Right? Millions of years old, that book. This book. Millions of years old. Evolution didn't start 2,000 years ago, 10,000 years ago. Evolution started 4.6 billion years ago. That's life. Life does that. And that's the way of life, good and evil. Yeah. Balance. The scale. Justice. That's what I'm talking about. your sword has two edges. It's always something like that. And then you know it, then you get it. Your brain is split in two even. And a coin, you flip it, it's got two sides. Everything's significant. And there's two sides on the same coin, remember that. Two sides on the same brain. And evil, good and evil. Logic, use logic, nothing else. Not an or statement, an and statement. They're both true or the statement is false. Yeah, and we know light is polarized. We know light is polarized. So let's look at what happens when we bounce them off the mirrors and see if that's what's really happening instead of bullshit interference. We have the light coming this way. This one is red, and it's going to transmit this time, so it just goes straight through. A little refraction. It might go and compensate for its own refraction through the medium and just continue on its way, I suspect. Now, when it hits, we had reflected. So let's see what happens when, let's for continuity, let's start with reflected. Comes here, hits a piece of silver, reflects. Let's just do this way. Let's put a little compass here. This is north, and this is the top of that pen is north. The tip, the ink. This is north. Positive. What do we do to say? Let's say north is, what do we want to say? I'm going to say negative. North is negative. It seems to be the standard. You know, you're polarized. Your idea of polarization is actually inverted, believe it or not. Okay? Always. That's just the beauty of life, I'm telling you. So you have it negative. You hit the piece of silver, boom, you're inverted. That's your first reflection. Now you're going up. Boom, you hit another reflection, boom, you're inverted. Boom, you hit another reflection, boom, you're inverted. And this time, you have a negative photon with a negative spin. A photon with a negative spin. I can't believe it. I feel like we're looking at electrons in air. I think that's what we're looking at. I actually believe we're looking at some form of electron. It's weird. My head is just boggled. So we have a negative. Let's try that again. Try this experiment again. And we're shooting a monochromatic light. We already know that it's oriented one way. And all the photons are going to be oriented the same way in this experiment. We assume, which is an assumption that should be proven actually to some statistical probabilistic certainty, some degree of it, that we've actually launched pure monochromatic light in the exact fashion we wanted it to. Make sure that laser's right on the money. Okay, now we shoot this one, and this time it's reflected, boom. Reflect again, boom. But this time it transmits, so we have a positive. This is like weird. I don't know what I'm doing. This time we fire this one, but it's transmitted, it doesn't reflect. Boom, it hits the reflection, boom, upside down, up. And what do we say the third one would be? Transmitted, up. So then we have a negative. Really? I'm gonna do that one again. Transmitted, goes straight through, one reflection basically. And we have a negative. Now we have transmitted, reflected, now we have a positive. Positive, negative, positive, negative, positive. Now what does it mean? It doesn't tell us much. The mirrors. The fact that this one hit 2, and then boom, and then this one hit 1. It still hits a mirror. Transmit. Okay, so we have reflected, negative. Reflected, transmitted, positive. Transmitted, reflected, or transmitted, negative. Only one reflection. Transmitted, reflective, positive. Okay. Now, if we change the length here, something happens. Something's gonna happen when we change the phase. They say when you change the phase, we can witness something else. When we make these mediums different for the light, all that stuff, it's like imaginary crap. I don't know. I can't imagine it. Purely imaginary. What's a virtual image again? They say you can deform a virtual image sometimes. And it's pretty complicated to form a virtual image, but you can do it. You can witness an image somehow. An upside down image somehow, I guess. Or a focused image or virtual image. It's not really there. You see it, somehow you see it, but it's not there. I don't know how. It's like I don't know. It's like a screen. It's like putting something on a screen. And you see it, you can project it on a screen. When you have a projection, that's kind of a virtual image. You're looking at the object you shine light on an object, and you can see the image on a piece of paper, and that's a virtual image. It's just light, made up of the light. I wonder. Well, I'm gonna cut it here because I'm getting lost. Getting majorly lost. There's a spin. And it's like an electron. It's not like an electron. So, if we fired one at a time, we'd see these. This probability. Generally, we'd have a 50-50 chance or a 0 chance on either one. Or 1% chance. 100% chance on one. What happens when we change the length? So the reflection doesn't really change the stats. Might be mistaken. Reflection doesn't change the stats, but when you change the phase, they say there's got to be a phase accounting for this phase difference. I would say there's a charge difference. There's a spin difference. A spin, but it can't possibly actually split the light. What the heck? They're really trying to say it's going both ways. We split one photon. How do we split one photon? That's what I'm trying to figure out. And they're trying to prove that there's a wave, that they split the wave. And somehow we don't know which arm it's in until we block one. So let's block one. We block one. Now, go figure, everyone, what happens to the transmitted? They're just absorbed. They just get absorbed here. Let's say this is a black body. This just absorbs. So half our results are going to land on one of these paths. So we still have 50-50. And if we block this one's open, we still have 50-50. But we have to do twice the amount of experimentation. We have to fire twice the photons because technically we're going to be absorbing on either side. So how do we get 70? I don't know. That's so bizarre. I can't see how it's going to get 75. That's so weird. I put pi in it. I swear I put pi over 2 in there. What's pi over 2? It's like half of it, right? Pi over 2 is half of it. We said that. What about this section here? What happens here? What happens here? It goes up a bit. It has to. There's got to be a bit of an up. If they're so sure about it, there should be a positive. A bit of a jump. Say 75. Let's say 75%. I don't know what's going on. Bizarre. I'm gonna cut it here and just see if I can make sense of this. Maybe I'll let it cook. Put it in the oven and let it cook over. I'm talking about. I always get excited at the end of these. Let's look at the time. We still have more time. There's plenty more time. Okay. Lots of time. Lots. Unfortunately, I have to switch this around. I'm not a pro photographer. And when I get a good angle of myself, I like to keep those pictures because I really get good ones sometimes. You gotta look at this ugly mug if you want if you want to follow along. Sorry guys, my bad. Okay, so let's just walk this through in theory. Something doesn't make sense. Something definitely doesn't make sense. I'll go with the idea that it's got to spin. What else do we know about electrons? They got energy levels. They run in orbitals. And they exist there's a threshold for every one of them. Now, surely when we hit one reflective surface, we lose something. We lose something. We have to. What do they say, intensity or the energy of the frequency, whatever, the power, the frequency of the wave. What frequency? Laser, what frequency? Are they all the same? Every laser comes in the same frequency? No. You have green lasers, blue lasers, red lasers. I gotta get into it. I gotta build this. It's the only way to do it. What if you did? What if you did lose energy on those reflective surfaces? I'm not doing anything imaginary. I can work this out imaginary. You want to do imaginary? You want to play like that? You want to play with imaginary numbers? Okay. I can do that. No problem. Let's dance. Let's dance, sweetheart. Come. Come see. Come learn. Teach you. No problem. Sorry, that goes all around. This is the garbage. I'm just messy and I'm meaning to get it clean as soon as possible. Let's do imaginary review. We're just gonna draw a circle because that makes life easier, and we're gonna have reals in our two-dimensional face space, imaginary and the real. So what do we say with cos? Cos is 0. If cos is 0, what do we say? How do we transfer this? I haven't done this in 3 years. What a joke. Who are you kidding? Here we have cos. Cos is this way. Cos seems to be real. Sine seems to be the y. Sine seems to be kind of like, oh, let's just shift it 90 degrees. Yay. Sure. So we have cos is 0 is 1. At cos is 1. We have 0. We have 0. Cos is 1, we have 0. Cos of 1 is 0 equals 0. Cos of 0 is 1. What's that? Cos of, I can't remember. Cos of pi over 2. No, cos of pi is 1 pi. Whoops, 0 pi. Let's make that right. Cos of pi over 2 is cos of pi is 0. Cos of 0 is 1, and cos of pi over 2 is here somewhere. I can't remember. It's a circle, whatever. Pi over 2, it's got to be 90 degrees. It's got to be equal. It's got to be 0.5. Just logic. Use your head. You're surprised what your head can do. I'm just getting out of my mind. Ever since I thought of that, I got a dirty mind, guys. I'm gonna try to hold it back for you, but I could really go for a little cha-cha-cha, a little sugar. I could use some sugar right now. I think my body needs sugar because I'm getting distracted. And I'm getting weak in the legs, as they say. And my loins shake, and my hip joints are going slack, and my knees are knocking together. Okay, I digress, but we continue. Okay. There we go. There's your sinusoid. Your cosine. Now we want to do this imaginary. So what do we have? We have 0.5, 0.5i, right? 0.5i, is that what that is? Pi over 2, pi, I don't know how that works. 1, yeah, this is just, it's weird. I get so confused. It's 0.5i plus pi over 2. Is that right? Or something like that, over 2. I think that's right. I'm getting so confused. That's this one. So what's happening in pi over 2? For all intents and purposes, and if this is mistaken, I'm not just going to upload this immediately. I'm going to double check this before I get into it. So when we say pi over 2, what's happening in pi over 2? Phase shift. Pi over 2 phase shift, we have this weird experiment. This weird example. We have some imaginary things. We said pi over 2 is a 50-50 chance. There's something happening. So we know something's happening here. But what's interesting, but we get this example here when they're pi out of phase. It's more like a destruction. What does that mean for our outcome? At pi over 2, we have a 50% chance. And this is a purely imaginary result. It's pi over 2. I mean, it's not purely, it is kind of imaginary. It's kind of, it's not really it's not real. And here we have this and this. What's the difference? What's the difference? 0 and 1. And then you can switch it from 1 to 0 if you want. You just subtract instead of add. I'm going to see where this goes. If you had a spin, let me switch that around again. Switch around, magic, done. If you had a spin, if you spin, one was spinning, you're just bouncing around really. You're bouncing around. I don't know. I don't know. I'm lost. So lost. It's a particle. It's not a wave. It's a particle with a spin. It's got an energy level, and that energy level is very dependent on the reflection. So we know not only that they're being reflected and they're being inverted. We also know that they're losing energy along the way. They're losing energy along the way, somehow decaying like that. Bounce, one goes off, one goes another way. The electrons move. And then you gotta account for that. That's a bit of kinetic energy it loses somehow. Elastic. It's all elastic, but whatever, they're bouncing. Let's assume they're bouncing. And they go to they hit the energy level they're supposed to. The energy level they're supposed to in the mirror. Which has got to be metallic. The only way is if it's impermeable, 100% impermeable to EM radiation. So it's got to be metallic, something like that. It's got to cause a current somehow. It's got to move a current, create that little, and somehow it just finds where, depending on where it goes now. The ones on the outside are more loosely bonded, so it probably hits the outside ones first. It doesn't go in and just hit the center of the nucleus. It probably nails the outside shell of the atom, and that's the first one to go, the first energy level. And then if it's a higher energy, which would mean the frequency is higher, has to be higher. Frequency would have to be higher. It gets through the first energy level and it hits the second one. Or it hits the first energy and knocks it all the way up. 2 energy levels, whichever one. Is if it jumps 1 shell at a time or 2. I think they jumped 1 shell at a time. That's the way we do it, just for simplicity. But if you give it enough energy level, it'll go bing, bing, and maybe hit another energy level, and it goes off up to the next one. It's like that, and something is going on there. And I want to see what really is happening. I want to build this thing. So stay tuned. See the time, and if we got good time, we'll quit. Almost 30. We'll do 30 minutes and then quit. Because 30, that means we got more to do. I'll tell you now. Okay, good luck and see you later.